Hello, I'm Susan Hutchison, and I'm in the NASA ISS Payloads Office, and I'm here to talk to you about the NASA cold stowage fleet and conditioned stowage fleet that we have to support science, transport, and on ISS. Next slide, please. The cold stowage fleet consists of passive and active systems. We have temperature range that we can support of plus 48 degrees to minus 130 degrees C. The systems are compatible with the shuttle, and they're compatible on ISS and with transport on Ascent for Progress, HTV, and they're going to be certified for SpaceX and the Cygnus vehicle for Ascent on Cygnus. The active systems we have are the Melfi, which you've heard about from Astrium. It's the minus 80 degree laboratory freezer for ISS. We also have a Glacier unit, which is a freezer unit, and the Merlin, which is a combination refrigerator freezer. And our passive systems consist of a coal bag and ice packs and ice bricks. Next slide, please. This is a picture of our fleet, of our active systems. You see the Glacier, it's a double mid-deck locker in size. Our Merlin is a single mid-deck locker. And the Melfi unit, it has 4 dewars, which are the round units, and this is a tray that's being pulled out by Jeff Williams. And inside the tray, we have box modules that we store the science in to keep them from floating out. So you'll hear those different terms, so I wanted to make sure that you understood what those were. Next slide, please. The Melfi rack, we have 3 of them on orbit. We plan to have 2 of them active at any point in time and a 3rd one available as a contingency. Right now we have 1 that's operating on orbit because of the pump failure that happened last Saturday. We consolidate all the science into 1 unit to preserve the resources on ISS. But as soon as that's repaired, we'll have the 2nd one back up and operating. On the ground, we have a training unit. We have an engineering unit that's a full mock-up of and full size of the Melfi, so we can perform tests with that are simulating on-orbit issues, problems, that type of thing. And we have a laboratory ground module, which is 1 dewer's worth, where we can do hold tests and science scenario testing. As I said, each Melfi consists of 4 identical dewars. They can be set at different temperatures, and the temperature ranges that are supported for the Melfi are minus 90 degrees C, minus 35 degrees C, and plus 2. The Melfi can hold up to 175 liters. At times when Melfi may need to be powered off due to reboosts and reconfiguration of fluid loops and that type of thing, the Melfi can hold for a minimum of 8 hours below the minus 68 degrees C. Next slide, please. It's just a little information about the size of our box modules. We have quarter box modules and half box modules. We are currently trying to get rid of all of our quarter box modules and replace them with halves because it's easier for the science to be installed in them and it's more efficient for our ice bricks and ice packs. Next slide, please. The Glacier is an on-orbit and transportation low-temperature storage. We have 6 of them in our fleet at the moment. We are procuring 2 more from the University of Alabama. They're building them to support the extension of ISS to 2020. And we have 1 engineering unit on the ground. These are used for active ascent and descent on the various vehicles. They will be used for ascent and descent on SpaceX. We've been working with the folks on trying to do fit checks and making sure that everything is compatible for that. And then we'll go up also on the Cygnus vehicle powered. We can get them up unpowered on a lot of different vehicles, but to support active science going up, those are the 2 vehicles that we'll have in the future. As I said, the Glacier supports temperatures from anywhere from plus 4 to minus 130. It was actually designed to minus 160 on ISS. We may be able to get to minus 160 if there's a requirement, but we will require additional power than is currently available to the express racks. The minimum cooling temperature is also dependent on the configuration. We can either be air-cooled and get to minus 95 degrees or be cooled on the thermal control loop, the water loop, to minus 130. And next slide, please. This is just a slide to show you how much science we can accommodate in the various locations. It is location dependent, especially in the mid-deck of the shuttle, but in the future that won't be as critical. We're still working with SpaceX to determine if they have a limit, a mass limit based on where we're going to be installed or whether it's going to be the design limit of the Glacier unit itself. So that's why that's TBD. And this just gives you some of the dimensions of the size payloads that we can accommodate. So as you're developing anything to go into the glacier, you can make sure that it fits. What we do ask in our cold stowage interface document is that you design to be used in any type of fleet asset. That way, if something has a failure on orbit, we can put you in a different fleet asset. So not to design to one specific piece of equipment. The power off time, if a glacier does lose power, is a minimum of 6 hours if it's 75% full and was at minus 68 before the power was turned off. Next slide, please. The Merlin, that's our single mid-deck locker capability. It's also used for transport to and from station and can be used on space station. It's a combination refrigerator, freezer, and an incubator. It can go from minus 20 on water cooling up to 48.5 degrees C. And we just put some information on about the maximum size and weight of payloads that can be accommodated in the Merlin. Next slide, please. So a little information about using the Merlin for active ascent. Any conditioned payloads would have to be installed at L-3 days, and that's typical of both the Merlins and the glaciers. And we make sure that there are no power interrupts of any more than 5 minutes as we transport it to and from the launch facility and also on return. Both the Merlin and the Glacier are early retrieval systems. We get them within 6 hours of landing of a shuttle. We're working closely with the next vehicles to work the scenario to make sure that we get them within a reasonable time to ensure that the science is under condition control all the time, power control. And this is just a history of some of the Merlin launches that we've had. Next slide, please. This is our passive systems that we're using mainly for transport to and from ISS. We have our cold bag right here. We also use it for transferring science samples from one refrigerator freezer to another one on orbit when we have a need to do that, like we did this last Saturday of consolidating all the science into one Melfi. Within the cold bag, we use a phase change material, and we have two different designs. One is called the ice pack, and that was our original design. We are phasing this one out, but you'll still hear that term quite a bit. And then the ice brick, which is our new design. It's a little bit more efficient for both storing inside of Melfi and for packing for return, so we can get more volume to come back. Next slide, please. As I said, the cold bag is a passive system that we use mainly for transport, but we can also do transfers on ISS using the cold bags. We currently have 14 in our inventory. We have ice bricks and ice packs of various temperature ranges of phase change material, and I'll get to that in a minute. The hold time for our bag depends on how much science is in there, how many ice bricks or ice packs are in there, and the configuration. So we do a test for each configuration for return and for launch to make sure what the hold times are, so we know what our limit of capability is. This contains some information about the size of a cold bag and the size of the experiments that can be placed in it. These are late stow items for ascent and early destow items for return. Next slide, please. Our ice brick, which is our most recent design and the one that we're migrating to for our entire fleet, consists of a solid phase change material and a hard plastic shell. And these are put together in groups of 2 with a bendable sleeve. This makes it easier for the crew to work with. These are available in various melting temperatures. Right now we have +4, -26, and -32, and we're investigating some alternate temperatures, and when those would become available, we'll let the community know about those. Next slide, please. And this is our old ice pack assembly. It's very similar to our ice bricks, same type of phase change material, just a different design, different packing. And as I said, we are phasing those out. Next slide, please. We have a cold stowage team that supports all of the conditioned stowage fleet hardware, and the services that are provided by this team is the on-orbit operations of all the powered equipment, oversight for the hardware development and operations, They perform flight preparations and offline operations. They handle all the hardware and cold stowage for, like I said, on orbit. They do integrated cold stowage performance analysis, and they do compatibility analysis for safety. This team consists of partners both on the NASA side of the JSC ISS Payloads Office and the Engineering Directorate. And then we have contractors that support us, which is the University of Alabama at Birmingham with the Glaciers and Merlins and the Jacobs Engineering Support Contract. Next slide, please. We have services that are available to the payloads community that are performed by this team. We have a laboratory over in Building 7 over at JSC that has various refrigerator freezers, and we can perform cycle testing. We can conduct our hold tests and other types of verification and compatibility testing that may be required by our payload developers. The team also supports all launch and landing operations for any conditioned stowage transport items and the science samples. We also perform crew training. We do cold skills training for the astronaut crew, cold bag and ice brick packing training, and the Merlin training. And then we have some engineering units for the Merlin, Glacier, and Melfi units that are here, so we can perform any tests similar to what would be done on orbit, but we can simulate them back here down on the ground.